nitrogen in all its wonderful forms. And so Dr. Mary Jo Kiersitz is going to start us off, and I think it's going to be a round robin like we just had for ours.
Yep. All right. Thank you, Des. Nice to see all of you today. So, as we said this morning, this is about all things nitrogen. We're going to talk about ammonia, nitrite, nitrate, nitrogenous disinfection byproducts a little bit. I would like to acknowledge my co-PIs, Jerry Spitel and Carrie Kinney from University of Texas, Dave Reckow and Toole Park from UMass, and Jess Brown from Carollo Engineers. But I also want to acknowledge people that are actually doing the work. My postdoc, Nahal. You'll hear from her shortly. Emily Palmer, she's a master's student with me. You'll also hear from her. We've been very fortunate to have kind of a little army of undergraduates who've been really keeping things going for us in the lab. That's Ethan, who's here, Abel, and they've been with the project since it started, and then Ryan just joined us this semester. And also Sumi Kim is the graduate student, PhD student, I think, right, from UMass. And so let's jump into this. So we're looking at biologically managing these nitrogenous contaminants. This is something, biological treatment is something that can be automated, which is attractive for small systems. And small systems, I'm sure Jess can touch on this when he speaks as well, small systems are interested in biological treatment. So we've broken this up into 3 sub-projects, the first one being nitrification. All right, so ammonium going through nitrite, going to nitrate. Denitrification is our next sub-project. Basically, you're taking nitrate, going through nitrite. You can go through these intermediate gaseous nitrogenous products on the way to dinitrogen gas. And our third sub-project is the nitrogenous DBPs. So basically taking precursors and forming nitrogenous DBPs. We're going to be focusing for the most part today on these first 2 projects, sub-projects. Most of our time will be spent on nitrification because that's where we spent the bulk of our effort in the work thus far. We'll talk a little bit about the denitrification side of things. We've just started these columns up in the last few weeks. And we're just going to touch on the nitrogenous DBPs for sub-project 3. Basically, the samples for that sub-project are going to come from the columns that we're running here for the sub-project 1 and 2, nitrification and denitrification. We're going to be doing those soon, but we haven't started that yet. So we'll just point out where we're taking those samples. So anticipated target utility characteristics, basically utilities that have a source water containing ammonia or nitrate. Of course, ammonia is not regulated, but nitrite and nitrate are, so this is why we're interested in this suite. And in terms of where we are on the continuum, we're here. We're developing concepts, and we're also going to be doing some piloting and demonstration. So I'm just going to introduce kind of the different pieces of this sub-project 1 on nitrification, and then my postdoc and student and Jess are going to be talking about the various pieces of this. So the first thing we wanted to do is to isolate and concentrate natural organic matter for use in our bench scale nitrifying filters. We're just trying to prevent having to deal with seasonal variation when we're doing these bench scale work. So John is going to talk about that, this concentration process. Then Mahal's going to talk about looking at nitrification at the bench scale for different NOM sources. We actually are doing a surface water and a groundwater. Emily's going to talk about this, the impact of soluble microbial products, SMP, and can we leverage them to actually get better trace organic compound removal by heterotrophs. And then Jess is going to talk about the pilot scale work that we're going to do in conjunction with a WRF project that has already started. I'm going to turn it over to John. And actually what John is going to be talking about is also in use in another project. Is that project C? Okay. So this NOM concentration goes for 2 projects. There's the pointer if you want to. You can stand in front of the microphone as well and project a little bit. Yeah.
All right. So my name is John Herbold. I'm a master's student in Des Lawler and Lynn Katz's group, where I helped out Mary Jo's group with this NOM concentration and isolation project, which was basically the purpose of this is to obtain a concentrated sample of natural organic matter for use in the nitrification experiments that we're going to be conducting, as well as, for example, Soyun's work in electrodialysis and reverse osmosis. So it's a relatively simple process with 2 steps, the first being the isolation of your natural organic matter, and that occurs through filtration, and then ion exchange to remove your cations, and then non-concentration, which is basically we use reverse osmosis system, but we keep the concentrated solution instead of keeping the permeate. Up here you can see the system right here with the membrane and ion exchange column. This is a system that was used for an EPA-funded project in the past here at UT, looking at treating stormwater runoff. And one of the big deals in stormwater runoff is heavy metals, and natural organic matter plays a large role in the partitioning or the complexation of these heavy metals, and plays a big role into their treatment. So they wanted to be able to isolate natural organic matter that's found in the environment for use in those experiments. So first off, I'm going to delve a little deeper into each of these steps. So the first step, the isolation step, like I said, starts off with filtration. And what we have are two filters in series, a 5-micron filter and a 0.5 micron filter. And this basically removes all your total suspended solids, thereby resulting in just a dissolved organic carbon solution. This reduces the fouling of your ion exchange resin as well as your reverse osmosis membrane. And then from there, your filtrate then goes through your cation exchange resin. And what we're trying to do is remove your metals such as calcium, magnesium, and other metals that may be in your solution in order to reduce the fouling of your membrane, as well as removing those compounds that could competitively adsorb to or complex with the natural matrix in your experiments later on. And the resin that we used here is a hydrogen formed strong acid cation resin. The reason you do that is that any other cation that would be released in this step would then be concentrated along with the natural organic matter, and then potentially precipitate out in your reverse osmosis membrane because of the hardness of the water. We found out that unfortunately it precipitated a bunch of calcium carbonate when we weren't monitoring the pH of our treated water well enough. So once you run the water through the filter and the ion exchange column, it's run into intermediate storage tanks. So we have tanks that hold about 2,600 to 3,000 liters of water. We have a big Bertha that we fill up. You guys have Bertha. Ours is about twice the size, and you fill that up. So we run that.
It's gotta have a bigger Bertha.
Yep, just have a bigger Bertha.
Everything's bigger in Texas.
Yeah.
Bertha's big system.
So essentially what it is, it's just a simple reverse osmosis membrane, and this solution that has only dissolved organic carbon with the cations mostly removed, we run it through this RO membrane. And the permeate we actually just discard, we get rid of that, but then the permeate, or the concentrate, excuse me, is then pumped back into those intermediate storage tanks, and then that's run basically in a circle, and concentrating that down to about 20 to 100 liters of concentrate. Theoretically, you can get above 90% recovery of that natural organic matter. So these are some of the results of this. I just want to point your attention to the dissolved organic carbon concentration. So we didn't actually, we were kind of hard pressed to get some water pretty quickly, so we weren't able to get an initial DOC value. But from this surface water, which comes from Lake Austin, this is also the source water for a bunch of Austin's drinking water, and so they report about 3.5 to 4.5 TOC, and so DOC is going to be a little bit less than that, but in the same ballpark. But we were able to concentrate that to about 270 milligrams per liter, which is about 70 times. And also, one of the things we were very interested in were those metal concentrations. You can see the ion exchange resin is working relatively well. The groundwater is a bit of a different story. it still concentrated it really well. This value right here is going to be a little bit lower, mainly for two reasons. The first being that there's going to be less natural organic matter in groundwater naturally, but also I believe this run we were only able to concentrate to about 100 liters. I think because near the end of our ion exchange run, our ion exchange resin was getting fully loaded, indicated by a slight rise in the pH, and so I think that's why we have these high values for our some of our cations. So we couldn't concentrate it as much as we would have liked, mainly because that osmotic pressure was getting pretty high, and we didn't want to take it to a dangerous pressure. So that's just an overview of this system and some of the results that we had from it. And then Michal is going to take it off from here and just show you a little bit of what this was being used for. Yeah.
Just one more thing, I wanted to make sure I clarified. So this system we actually got help from EPA developing this. This is based on the work that Jonathan Pressman helped us out quite a bit to look at this system. And so that we simply modeled our system after theirs, but it's the first time anyone's ever applied it to trying to collect highway runoff, which is unique in and of itself. And then the other thing I'll point out is one of the issues with this system moving forward, Mike, you probably know this, is sulfate.
Sulfate, I was wondering if that was used.
Yeah, and so one of the reasons we did not want to freeze dry this is because especially in the groundwater, the sulfate concentrations are really high. The reason we don't have numbers for them is that they're basically, we have to go back and run ion chromatography in a different mode to be able to get it because it's so large in the concentrate. So I wanted to point out the issues with sulfate when you do that. I think in our highway runoff we precipitated barium sulfate.
Yeah.
We ended up with too much barium in the water.
Yeah, I think Jonathan used barium sulfate.
Right.
Answer, no,
Yeah,
yeah.
to get rid of it.
Video.
Yeah,
It's a challenging one to do.
It's a challenge of
Yeah.
it.
But one of the things we want to do with this next, and I don't know if you guys have done this.
Here, actually,
is
hit share screen.
is potentially
Right there.
build like
No, actually, isn't in.
That's in the call.
getting rid of some of those.
Is this what Mike produced?
Mike produced there.
Yeah. Yeah, but
Have you talked to him?
I looked at his stuff. I talked to
Scott.
Jonathan about it.
Yeah.
I talked to Jonathan about it.
Scott,
I don't know.
Yeah.
you can hear us?
Done such
I can barely hear you. I'm gonna try to turn
Yeah,
up
I
my
think it's a little
volume.
rough.
How about now?
It's still pretty low.
Pretty
Anyway,
low.
I mean, the process.
Can you
the
hear
reason I'm
me?
bringing up
I can hear you
is
just fine.
because this is a really great process.
Let me
To
see.
be able to get known for a project
Yeah,
that isn't gonna change
Let me
over
try
time.
some.
yeah, right. Oh, no, that's really
Yeah.
nice.
And so,
But you'd like not to have that all of a sudden.
yeah, but the
No,
sulfate.
it's fine.
It's fine now?
Right.
Yep.
Okay, wonderful.
Right, and didn't Jerry Lanier have a way of getting rid of sulfate? He did some sort of precipitation.
I think he did precipitation.
Yeah.
The problem with that is then you end up with a bunch of, you have to do it so carefully.
Yeah.
Like add it little by little so that you don't end up with a bunch of barium
Excess
in the
barium.
water, which is what happened. Which is what happened with our highway runoff. It didn't affect our results there because we were adding a bunch of.
Okay, Scott, there's just a few people asking questions, and then we're going to continue this presentation.
Okay.
Linda,
Thanks.
you all set?
I'm done,
Yeah,
sorry.
there's two questions. I assume the RO, it's a single pass through, and what's the recovery from a permeate flow versus feed flow perspective? And single element, single pass?
It's not a single,
What's that?
it's not a single pass.
Well, I guess it's not
Well-
a single pass in that we're basically refiltering the same water that we're
I know,
concentrating.
but from a process perspective, the flow's in, the flow's out. and
Yes.
It's not going to another membrane, a different
No,
membrane. So
no.
it's a single pass.
Single
It's a single
pass,
pass.
single-
So what's
single
the
cell.
permeate flow versus the feed flow?
I would, at least when I was running it, I was shooting for 90% permeate, 10% concentrate.
Nope, you're not hearing my question. So my
Okay.
question is, what's the feed flow to the feed side of the membrane and permeate flow?
Oh.
Thank you.
I don't recall what that was, right off the top of my head.
So
And I'm not sure if that was very well
So usually when we say recovery or non-aerobic, that's what you mean. So does 10% of the feed flow go through the permeate? That's the recovery of that element, that specific element. So I was just curious if it's one, where does it lie in the realm of which these things operate? So, in the membrane?
Dow.
NF270?
Say that again?
NF270 is a softening membrane. It's probably tighter than that.
No. Yeah, it was. I can't recall the exact model. I have it on my computer. I can look that up for you.
I assume that would be a tighter.
How many liters do you think you'll need to get?
Well,
Well, I guess it depends on the final concentration of the
yeah.
Hi, good afternoon. I'm going to talk to you about the status of our bench scale nitrifying biofilters for removal of ammonia and trace organic contaminants. And I'll start off with just a really brief refresher on nitrifying biofilters. So there's two primary processes, and both of these are oxidation processes. So the first one is, of course, the nitrification, which generally is a two-step process, but not always, of ammonia to nitrite and then oxidation of nitrite to nitrate. And the nitrifiers that carry out these processes are, again, generally autotrophic, slow growers, and they are non-modal, which means that they really need a good biofilm in order to thrive. The second primary process is the one that you would typically find in your full-scale biofilters, which is oxidation of biodegradable organic carbon to carbon dioxide. And I'll point out that the organisms that do this are the heterotrophs, and I'll point out that these organisms also need some kind of nitrogen source, and so if ammonia is available, that will be their first choice, and that's how they produce their biomass. These organisms, in contrast to the nitrifiers, are fast growers, and they produce really significant amounts of biomass. So you can imagine that this can create a really good partnership, the nitrifiers and heterotrophs. But there's also a problem that the heterotrophs also compete with the nitrifiers for oxygen, ammonia, and space in the biofilm. So ammonia, as we all know, is a ubiquitous contaminant, and itself it's not regulated, but one of the problems that comes in with ammonia is nitrification in the distribution system. So besides the fact that it can produce contaminants that are regulated, nitrate and nitrite, there's also many other issues that come up, including formation of nitrogen disinfection byproducts, corrosion of copper and lead pipes, loss of disinfectant residual, growth of pathogens, and many other issues as well. So that's why we care about it. And trace organics are becoming increasingly problematic in natural waters, and they are often found with ammonia, and they'll probably become more problematic with population growth and as we go towards direct potable reuse. So because we find them together, it could be a really good place to see what kind of impact nitrification could have on removal of trace organics. And I should point out that there have been lots of studies showing in biofilters, just your typical biofilters, that trace organics can be removed. So let's see what happens in nitrifying biofilters, how it affects the removal. So in typical biofilters, there's two main mechanisms for removal of trace organics. The first is through sorption onto organics. So either onto your organic media, it can be on your natural organic matter, onto biomass in the biofilters, any kind of extracellular substances that are produced. And the second mechanism is through biodegradation. And it's important to note that the concentration of trace organics is 2 to 3 orders of magnitude less than the BDOC that's in the water. So these processes, the organisms are not using this as their primary source for growth. It's either through secondary utilization or through co-metabolism, which is it's just fortuitous reactions. The enzymes happen to be around, and you just knock into the compounds and degrade them. Okay, so onto our study objectives and design. So we're interested in looking at 4 different objectives. So the first one is the impact of using 2 very different sources of natural organic matter, so groundwater versus surface water, and looking at how this affects removal of ammonia and trace organics. The second objective is looking at the changes over time to the microbial communities. The third is the robustness to perturbations, both for nitrification and trace organics. And then the fourth one, and this is where UMass comes in, is that's the main place where they come in, is looking at formation of the nitrogen disinfection byproducts. In this presentation, right now we've really been focusing on just getting really good steady nitrification, and so that's what I'm going to be showing you for now. Okay, so this is, it's a little bit fuzzy, but this is our setup in the lab. So we have our influent tanks over here that are stainless steel. Whenever you're working with trace organics, there aren't very many compounds that you can use. They'll sorb onto lots of things. So you have to work with either stainless steel or PTFE or glass. So we have stainless steel influent tanks, and then with a peristaltic pump, we're going into our columns. And we have 4 different conditions set up in parallel, and each one has 2 fixed beds in series. And so you can see over here, and then there's 3 sampling points, so at the influent, midpoint, and effluent. So as we had mentioned before with John's presentation, our original intention was to use, or our intention is, to use our concentrated natural organic matter, but it took a little while to get that all figured out, and so we wanted to get a little bit of practice in the lab with our biofilters and working with nitrifiers. So we did a first run where we just used our raw waters, and we did do a settling stage just in a cold room to make sure that large particles came out, so that our turbidity was around no more than about 1.5 NTUs. And so we had, for our setup, so we had 2 of our columns with surface water, 2 of them with groundwater. The groundwater naturally had ammonia, and the surface water we amended with ammonia, and then we also amended with a suite of 10 trace organics. And in order to assess whether the removal of the trace organics was through sorption onto the organic media, the GAC, we had a no sorption control for each of the water types, where we used sand media. It was Ottawa sand, which has very low levels of organics. And each of these biofilters, you'll keep seeing throughout the presentation that I'm saying 10-minute simulated EBCT, or total 20 minutes simulated. So we used a scaling model to simulate what it would be at the full scale. So at bench scale, it's I think around 3 minutes, and then at full scale, it should simulate about a 10-minute EBCT for each of the biofilters. So the suite of trace organics was selected based on various factors, including covering a range of uses and types, various chemical classes, and also ease of biodegradation, between very easily biodegradable, like 2-MIB and geosmin, to pretty recalcitrant, like gemfibrozil. Okay, so on to mostly our ammonia data from run 1. So first I'll show you these were some of the, I guess, the important water quality parameters for our groundwater, which was from the Edwards Aquifer, collected at the Wildflower Center in Austin. And then the second one was the surface water was from Lake Austin. And most of these parameters are pretty typical for groundwater or surface water, but I'll point out the huge differences between the 2 water types for the organic material. So the dissolved organic carbon was, again, pretty typical. The surface water was really high, and this was done over the summer. We had very strong rains here for a lot of the summer, and that's probably why some of the time it was really high levels. And you can see also the assimilable organic carbon was in a pretty typical range for groundwater, but really quite high for the surface waters. Okay, so here's the nitrification data for the groundwater. And on the y-axis, you see the percent removal of ammonia, and on the x-axis, you have days. And over here, we have, this is with the GAC biofilter, and over here is with the sand biofilter. And then the dotted lines in both of these are the simulated 10-minute empty bed contact time, and the solid lines are the 20-minute empty bed contact time. So if we look at this, the first thing that is immediately apparent is that the GAC biofilters achieved pretty much complete and stable nitrification with the 20-minute empty bed contact time, whereas the sand biofilters had very low removal, which we'll speak about in a moment. For the GAC biofilters, right where you see that circle, is where we started to see production of nitrate and nitrite, so we knew that there was nitrification going on and not just assimilation of the ammonia to make biomass by the heterotrophs. And then there were a few places where we had various disturbances. That's where the arrows are. So over here, we doubled our flow rate to get to the flow rate that we wanted. And then over here, because of some changes that we wanted to make to the columns, we actually took our media out and then we repacked it. But what's interesting is that over here there was this dip in performance. But later on, with the 20-minute simulated empty bed contact time, we actually didn't even see any kind of issues when we had the disturbance. You can see it with the 10-minute, but not with the 20. So the biofilters are really performing well. For the sand biofilters, we suspected that because the concentration of AOC was quite low, there was just not enough biomass accumulating on the sand, and so the nitrifiers had a really hard time growing. And so we wanted to test this out, and so we added for a period of time some assimilable organic carbon at a couple of different points. That's where you see these arrows over here. And again, we have the ammonia removal on the y-axis, time on the x-axis, and over here the red is for GAC and the blue is for sand. And so if we look at the sand biofilters, over here we added a bit of AOC, and over here we added it. And both times when we added it, we started to see an increase in nitrification. And over here as well, we saw an increase in nitrification. We didn't add it, we stopped adding it, so we didn't actually see the nitrification increase. We're just kind of testing this out. But our hypothesis seems to have been correct, that it was an AOC problem. What was surprising to us is that we added, this is really a pretty small extra amount of AOC, but when we did this, we started getting pretty unstable nitrification for the GAC biofilters, and we're a little bit puzzled about what was happening over there. So onto the surface water nitrification. Over here again, we have ammonia removal in days, and the sand is blue and GAC is red. So what's apparent over here is that the nitrification, we see nitrification actually starting from this point where you see the circle, but it was really very unstable throughout, and it looked the same for both of the biofilters, and this one again is where there was a really high amount of AOC, and we had those same disturbances to these biofilters as what we had to the groundwater biofilters. And what was interesting over here is that, so these two biofilters reacted the same to the disturbances, except that eventually the GAC biofilters seem to fare better. So again, it probably is a better attachment surface. They can thrive better. But these issues of what was going on over here related very likely to the AOC was probably a combination of clogging issues. We had a backwash a whole lot more. We probably had some short circuiting. And then the other issue was that our DO levels, we can see a correlation with the dissolved oxygen getting lower, and that affecting very likely the nitrification. And so, of course, in the field you would supersaturate your feed, and in the lab it's more difficult to do. We might have a way of doing it, but we did not do it in this case. Okay, so our conclusions from our first run were that the high concentrations of AOC in the surface water are going to cause this unstable nitrification. So with our reconstituted natural organic matter, we're going to use concentrations that are more similar to the groundwater. And the sand biofilters resulted in low or unstable nitrification. And so we decided that sand is not going to serve for us for a good no sorption control because the nitrification doesn't even look like what it does for GAC. So it's not really serving its purpose. So we're decided to use only GAC biofilters. So on to now we've set up our new biofilters now that we have our natural organic matter that we can reconstitute. So here's our updated plan. So now we're using our reconstituted organic matter at 1 milligram per liter of DOC. And again, we have either surface water or groundwater. And we're amending with trace organics. And what we chose now is for our ammonia, for each of our water types, we have no ammonia control so that we can look a little bit more closely at how we can say something a little bit more clearly about how nitrification specifically is affecting removal of trace organics. So for each of them, we have with and without ammonia, with and without ammonia, and these same 10-minute empty bed contact, simulated empty bed contact times for each of the biofilters. So our stages are of this study are inoculation with raw groundwater, that was about 2 weeks long, then acclimation to reconstituted water for about 2 months, and then various robustness tests. We're still finalizing exactly what those are going to be, but we definitely want to do some system shutdowns and kind of repeated system shutdowns, and then also changing our phosphorus concentrations, and then we may do something else with the organic concentrations, but we're still kind of deciding. And then the last part is, again, to assess this sorption issue versus biodegradation, we're going to add sodium azide, which inhibits microbial activity, and we'll do that for about a week to see how that affects removal of the trace organics. And so what we are doing is, for our analytical analyses on twice per week, we measure ammonia, we measure weekly a whole bunch of other things, nitrate, nitrite, pH, DO, turbidity. Monthly, we're measuring trace organics, DOC, AOC, and nitrogen disinfection byproducts. And then we're also taking samples for microbial and community analyses on a monthly basis to look. We're going to be doing fingerprinting using MySeq Illumina, and then looking at abundances with qPCR. And this is both of the 16S RNA gene for Bacterium archaea, and then also at ammonia oxidizer genes. Actually, that's it. So, and yeah, we're continuing from there, and we're hopeful this time around. So, and I think Emily is going next. Or, oh, yes.
Quick question.
Okay.
Really
Yeah.
quick. So the groundwater you said had naturally occurring ammonia,
Mm-hmm.
but you had some tests of groundwater without ammonia?
So when this one, so this round, because we're doing the reconstituted water, the ammonia has gotten removed. Yeah.
And then the azide does sometime, yeah, if you could, it's important, I guess, to tell us how much you're adding, because it reacts and forms some strange DBPs.
Oh. Okay.
And it'll interfere a little bit with some of our DBP
Okay.
analysis.
So I guess the only time we're going to be adding that is in that last week,
Uh-huh.
and I don't know if we need to do any DBP analyses,
right.
just for the trace organics.
Right.
Yeah.
Good.
Okay.
Can you explain the
This is Scott.
simulated EBCT?
The simulated?
Yeah, as
So-
opposed to just EBCT, why is it simulated?
Okay, so the actual EBCT is close to about 3 minutes, but if you take into account, if you wanted to do a scale, we wanted to make sure that our data that we're using, so often in the literature, if you see bench scale studies, you'll see like 8 minutes or 10-minute EBCTs, and at full scale, that's like really, really huge. And so what we wanted to do was choose a lower value so that if you scale it up based on like the particle size and the amount of biomass that would accumulate, it would be more representative. Obviously, it's not the same thing, but more representative of what a full-scale plant would look
so
like.
you're scaling based on the amount of biomass.
It's like an RSSCT.
It's
Okay.
okay. Scott had a question, I think. Scott?
Yeah, were you adding the trace organics during this phase?
Yes.
And how were you delivering them? Were you using a solvent to add them to the system?
So the trace organics are in water. Yeah, so they're at a higher concentration, and then we add them at a 1 in 1,000 dilution to our influent tanks. And the amount of carbon that's being added from that, because we had to resuspend our 2 MIB, I want to say, in methanol, but we added the absolute smallest amount so that it only ends up being 5 micrograms of carbon per liter.
Could that explain some of the AOC, high AOC values that you had?
That one, so in the other one, those AOC values are actually from our natural waters. So that was not with trace organics added.
So with the trace organics, then you're adding another half a...
We're adding...
You're adding 500 micrograms, half a milligram of DOC to the system?
We're adding only 5 micrograms of carbon per liter.
5 micrograms, thank you.
Yes. Yep.
Great, thank you.
Thanks. So keeping with the nitrification, this will be pretty quick because we just started this pilot 3 weeks ago. I guess I got to change it here, right? This work is being done in conjunction certainly with the Wind Center, but also with the Water Research Foundation. There are actually 3 PIs, 1 PI and 2 co-PIs that are serving on a project that we are leveraging with the Water Research Foundation. This project is 4559, the simultaneous removal of multiple contaminants through biofiltration. Eric Dickinson with Southern Nevada Water Authority is the PI. I'm a co-PI on this. Oren Schneider's a co-PI on this, and Scott Summers is a co-PI. So we have pretty good representation here. And as
Thanks for joining our project.
As we were thinking about the separate task of doing a pilot study specific to the WINS project, everyone knows how much is involved with that. There's this pilot study that we're doing in a number of places. No reason not to leverage that and get more out of both. So all I'm going to show you is kind of what the existing scope looked like for that project, what the pilot looks like that that's operating now, and then the scope that we're adding to this as part of the WINS project. So the first part is really being handled by Scott and his crew. It's a literature review, really trying to understand. You have something, Oren?
No.
Stretch it. So jump in, Scott and Oren, anytime. There's been so much work done on biofiltration, in particular in the last 10 years, in characterizing removal of multiple contaminants, a lot of trace organic contaminants. So this first task is really gathering as much of that information that's already been gathered. The research that's been done, the kinetics, the coefficients of degradation, the removal rates under different conditions. So that's task 1. And then Scott's group is really focusing on the CEC indicator compound assessment, trying to get the best indicators that we can to represent as wide range of these microconstituents as possible, because everyone knows how much cost is associated with the CEC analysis, trying to just ease some of that evaluation side of microconstituent removal. And then task 3, and this is where this project comes in right here. There's going to be 3 sites of pilot testing, 2 in Nevada at Southern Nevada Water Authority, and that's a wastewater impacted raw water, and then 1 here in Texas at Houston. The target contaminants that the project will be looking at, of course, is TOC or DBP precursors, but ammonia, N-DBP precursors, taste and odor, pharmaceuticals, personal care products, and manganese have really kind of been identified as the main contaminants of concern in these source waters. We're focusing the piloting on the impact of media type. There's been a lot of discussion about this over the years, and you've seen a little bit of that impact on the work Mihal just presented. Empty bed contact time, really the driver. Surface loading rate or loading rate is really not the driver when it comes to biological treatment. The filtration aspect for sure, but not the biological degradation aspect. So we'll be looking at the impact of that. looking at high concentrations of some of these contaminants. And then upstream treatment, whether you've got some kind of preoxidant, how do you operate your coagulation process? Do you have ozone? Do you not have ozone? Task 4 of the project is full-scale biofiltration testing. This is where American Water heavily comes into play. So we'll be looking at, tracking the operating parameters and the associated removal of different compounds across a lot of their plants. How many different plants are you guys going to be?
Well, we're using a couple of different plants. We have set up in around Philadelphia and also around Davenport, where we're using utilities that don't have biological filtration right across the river. So water quality is similar. And we're kind of trying to ferret out what's biological and what's non-biological.
And then we have a bunch of other plants around the country where we're doing full-scale testing. North Carolina, for example, is one that we're involved with. And then John mentioned this a little bit earlier. We want out of this is some nice tools that utilities can use. Now, this project isn't focused per se on small systems, but everything that comes out of this will apply to biofiltration, which applies to small systems. And so there'll be a toolbox of guidance and monitoring approaches, et cetera, that we recommend out of this work. Here's a schematic of the pilot facility here, or in Houston, excuse me. You've got 2 different source waters that you can use, either Lake Houston or Trinity River through the Coastal Water Agency. That can be blended in different ratios if you want. Comes into the pilot plant, and then you basically have your conventional, then into ozone, then into filtration. There are 2 parallel, well, actually there are 6 filters that you can operate, so you have good opportunity for control and looking at different conditions. This can be backwashed with chlorinated water or without chlorinated water, which is going to be another focus of the study, is the impact of chlorine in the backwash. Just a couple shots. Here's your raw water blending station, where you got the 2 different source waters coming in to the plant here. The flock sed is here. You can't see here. There's your plate settlers right here. 2 parallel trains. And then here's the heart of what we care about, but the whole thing's going to be running. This is really hard to see. I haven't been to this plant, and it took me a while for Greg Pope to kind of walk me through what all is going on. Back in the background here, there are the ozone contactors. You see how scaled they are with ferric. These are not operational right now, but we got to get them operational because that's an important part of the study. But we'll look at the non-ozonated stuff first. And then you see 3 columns and then 3 more behind, or you could see if you were right up on top of it. They're the different bed depths. You'll be looking at different things across well, basically 2 controls and 2 variable operated filters right next to it. Pretty cool pilot. There's a lot of automation to it, but a lot of things going on. It's a pilot that they have already built. It's one they use full scale at the plant to simulate the full scale facility. So this is where the WINS project comes in. All that piloting that we're going to be doing, we're going to be adding a lot of microbial analysis. This is going to be done at Texas, and I believe Amherst is also doing some of this work in here as well. Microbial community analysis, tracking the communities of the microbial communities as we change conditions. One of the things that we find over the years is that it's not necessarily super easy. It'd be nice to be able to kind of dial in an operating condition and tie that to a particular microbial community that you can then say ties into a certain performance. But we're still really working on that linkage. But even as we work on that linkage, one of the things where this really comes into play is with regulators, is that we find as we're able to identify the communities are there, the regulators and the operators and owners of plants really appreciate the microbial community analysis, kind of takes away some of that black box feel to biofiltration. A lot of work been done on the impact of phosphorus and phosphorus limitation. So there's going to be some phosphatase analysis during the study under phosphate limiting and non-phosphate limiting conditions to kind of, and then tying that into performance. EPS, when we talk about the hydraulics of a biofilter, it's the EPS, extracellular polymeric substances, that can really drive that, not so much bacteria, but the sticky stuff, the biofilm. So there'll be EPS and biomass quantification. And then this was really added into, there's a robustness testing phase of the piloting, but we've added some system shutdowns. You talked earlier about the fact that small systems are operating on and off and on and off, and that's what this is going to be. We're going to shut the system down, turn it back on, and see how it impacts performance as well as some of the other parameters we're tracking. And then the last task here is this being done at Amherst. This is the distribution system simulation with the annular reactors. Nope.
This will be done in Texas.
Texas.
Yeah.
Sorry.
This will be the same.
Okay. So they'll be using an annular reactor, really looking at the impact of a biological nitrifying system that's been chlorinated for final disinfection, what happens with respect to disinfection byproducts and the microbial community out in the distribution system. Oh, there we go. Analytical work being done at UT and at UMass. And the real nice aspect here is that even though this is going to really focus on the Houston project, we've got 2 other pilots going at Southern Nevada Water Authority, and we have a bunch of full-scale information. There'll be good information transfer across this project, across the 2 projects. So we ought to gain a lot, I think, for the WINS project for 4559 and vice versa.
That's great.
All right.
Jess, I just wanted to comment that the pilot plant in Houston is larger than any of the small systems we're talking about.
Right. Yeah.
Yeah.
What is the flow rate and what kind of system would that?
I should know the answer to that question, and I don't. Looking at the size of those columns, knowing that and the depth of those columns, we're probably going to be operating in the 5 gallon per minute range, 3 to 5 gallon per minute range. That's my guess.
So could we possibly scale this for the mobile, the trailer?
There's a lot that we can contribute to that mobile trailer. We have, Corolla alone has two of our own biofiltration pilots, and we run a lot of others. As soon as we started to talk about that earlier, my wheels were spinning. We've learned a lot of what to do and what not to do in terms of filters and pilots, and especially when you're trying to containerize them and things. So yeah, there's a lot we'll get. Next, all right, here we go, Emily.
Can I ask before you go on, what the distribution system simulation area, how's that set up?
We're going to do annular reactors, we're just going to bring water in and put it in Houston and just run it on the
It's gonna be like batched.
Yeah, we had thought about, I forget which one of you said they were taking the pilot right out, trying to keep it intact and taking it to various places. We had thought about doing that, but it's kind of a mess in terms of a student out there to sort of staff it during that time, so we could bring water and just in batches.
You're just gonna age it in the lab?
Yeah, like once a week.
So you're not really interested in the pipe in there, you're just interested in the biological
right, in the
aging.
microbial community.
Okay.
Yeah.
Not really the same lab.
Well, it is going to be, they're in biofilm studies, it's we're running on coupons.
Oh, okay.
Yeah.
Alright. Okay,
Yeah,
that's
so
what
we
I was
have,
asking.
yeah.
Where is this? How is that like a pipe?
Oh, yeah, yes, we're running it in annular reactor, so we can just choose basically it's a rotating drum, you choose the velocity. to simulate
Different kinds of
distribution system.
coupons?
We're only going to use one kind of coupon,
Hi, so I'm Emily and I'm going to talk about the last bit about nitrification, which is the impact of soluble microbial products on trace organic contaminant biodegradation. And the question that is driving this research is whether soluble microbial products, or S&P, produced by nitrifying bacteria aid in the removal of trace organic contaminants by heterotrophic bacteria. So a bit of a refresher on S&Ps. They're essentially the byproducts that are produced during microbial metabolism or biomass decay or the hydrolysis of EPS. And this schematic kind of shows how during a cell's life it might produce S&P as it uses substrates or as it produces EPS or creating a biofilm, and then the EPS goes through hydrolysis. And all of this makes S&P. And so by this definition, you can kind of tell that S&Ps are very diverse. And so they can be humic substances, proteins, carbohydrates. They can be really small, they can be very large, but they all contain carbon and electrons. They can be produced by heterotrophic microorganisms, which use organic carbon as a carbon source, and they can also be produced by autotrophic microorganisms, which use inorganic carbon as a carbon source. And so the autotrophic microorganism that we've been focusing on this whole presentation is nitrifiers, which use ammonia as their electron donor and carbonate as their carbon source. And so the key property of SMPs is that they are biodegradable, and that the SMPs produced by nitrifiers can be used as a carbon source by heterotrophic bacteria. So this was showcased very well in this study done in 2004, where they had a reactor and they fed it only inorganic carbon. And after a few months, they did a microbial community analysis and found that half of the microbes in there were heterotrophs. So the only carbon that they could have been eating was this SMPs produced by the nitrifiers. So heterotrophs and nitrifiers have a symbiotic relationship. So our hypothesis is that SMPs aid in the degradation of trace organic contaminants. So when heterotrophs use these SMPs as a carbon source, they need enzymes that are capable of degrading these complex carbons. And trace organic contaminants are complex carbons as well, so potentially these enzymes could serve a dual purpose for degrading these trace organic contaminants. But in addition, the SMPs also provide another carbon source so that the heterotrophs can grow more abundantly and are more active. So to test this hypothesis, I needed SMP. So I used a fermenter, and the fermenter had a 2.5 liter vessel where I could grow the nitrifiers, and I used Nitrosomonas europaea, which is a modeled nitrifier that's typically used in laboratory study. And I shield them from light because they're very sensitive to light. I supplied them air that was filtered through a 0.2 micron filter that was bubbled into the media. I agitated the media so that the oxygen in the air would diffuse more readily. I kept the temperature at 26 degrees Celsius, which was right in the middle of the optimum range for growing Nitrosomonas europaea. And I maintained the pH at 7.8. And this was key because during ammonia oxidation, the pH goes down. However, the nitrifiers would die if the pH dropped below 6. So as the pH would continue to go down, the machine would continue to add carbonate. And so it actually served two purposes, where it supplied them with more carbon source and it would raise the pH. So the nitrifiers in this system had unlimited electron acceptor, the oxygen, and they had unlimited carbon. So the only limiting substrate was ammonia, and the initial concentration of ammonia was 890 milligrams per liter, and I ran it until it was under 1 milligram per liter. And then it looked kind of like that. So it was very, very turbid. And I filtered that through a 0.2 micron filter, so that removed particulates and all the biomass. So all that was left, since it was only fed inorganic carbon, was the soluble microbial products. And it had a final carbon concentration of 5.6 milligrams per liter. So now that I had my carbon source, I acclimated heterotrophs, and I got the heterotrophs from the backwash of a biofilter to a simple carbon, acetate, and a complex carbon, the SMPs. And then once they were acclimated, I spiked them with trace organic contaminants, and I monitored the degradation of the trace organic contaminants over time. So my initial design was to have 4 flasks with the simple and the complex carbon, and then I had a control which was heterotrophs that were autoclaved, so there was a killed control. And then I also had a pure culture control to test whether it was a shift in microbial community, whether the SMP is only selected for microbes that could survive off of them, or if it was a shift in the actual metabolism of the microbe. And Pseudomonas is a ubiquitous organism, and it's used in a lot of laboratory study. And so I acclimated all the flasks for about 2 weeks, and I kept changing out the media so they had fresh carbon. And then I spiked it with geosmin and monitored over a week. And these were the initial results, which, if you look, is not what you would expect, since the most removal was by the killed control. And so, we thought about this for a bit, and kind of came to the conclusion that most likely my method of creating a killed control probably wasn't the best, which was autoclaving them, putting it up to a high temperature and pressure, so that lysed the cells most likely, which made a lot of sorption sites because there was a lot of cell guts. So to test whether that was what happened, we have a new experimental design of 10 different flasks. And so there's still the same heterotrophs and S&Ps and heterotrophs and acetate, but now we have 2 kill controls by autoclaving and using azide, which would hopefully keep the cells intact but kill them, as well as autoclaving. And then we're going to do the same with Pseudomonas to, gauge acetate versus S&P and the 2 kill controls. And in addition to that, we are going to look at whether just the presence of nitrifiers aids in the removal of trace organic contaminants. So we have a flask with S&Ps, heterotrophs, and nitrifiers, and a flask with just S&Ps and nitrifiers. And I actually did this study over time this last week, and I'm running it this afternoon, so I don't have new data for you. I'd have it Wednesday. But I will be presenting it at Texas Water in April. So the next thing I'm going to talk about, I'm going to switch gears to denitrification and the mitigation of nitrate accumulation in denitrification biofilters at low temperatures. And the research question for this is, does a micronutrient addition to denitrification biofilters ameliorate nitrate accumulation at low temperatures? So denitrification is the reduction of nitrate to nitrite to dinitrogen gas, and it can be affected by a lot of factors, including pH outside of the optimum range, nutrient limitation, dissolved oxygen, but we are specifically looking at temperature outside of the optimum range. And it's been shown that nitrite-reducing bacteria are a lot more sensitive to low temperatures than nitrate-reducing bacteria. And this is a problem since the maximum contaminant level for nitrate is an order of magnitude lower than nitrate. Yes. And the enzyme that's responsible for the reduction of nitrite is iron or copper based, so we're going to test if adding iron or copper to biofilters that have nitrite accumulation might mitigate it. So this is the current setup right now. I have a nitrogen tank that is bubbling into a carboy full of synthetic groundwater that has 1 milligram per liter of nitrate and 4.5 milligrams per liter of acetate, which is 110% of the stoichiometric dose. So that would ensure that theoretically all of the nitrate could be reduced to dinitrogen gas. And this is being pumped into 2 biofilters in series. And I use the same scaling method as Mahal. And my empty bed contact time is 1.6 minutes, which is supposed to simulate a 5-minute empty bed contact time.
Questions for Emily before I get to the last slide?
I have one question that goes to both. The EBC-CT scaling that you're doing here, or you mentioned biomass based, I mean, is it just RSS-CT scaling based on carbon size and HLR?
It's not. It's a, maybe Mahal, you want to talk a little bit more specifically about it. It's a maybe 10 or 15-year-old model. It came out of Bruce Rittman's group. For some reason, it never really caught on. But we're testing it here, and actually I'm doing just starting a collaboration with the University of Toronto where we're actually going to test and see how does this do in a drinking water setting. Does it really scale well from this bench scale up to the full scale? Do you want to speak a little more specifically about?
The medium is small, right?
It is small, yes.
The medium is smaller.
Yes.
Is smaller than what you would use in a full-scale plant, right? So that you have your I can't think what the term is, but
Specific surface area.
Sorry.
Is it specific surface area based?
Yeah, so that, well, so you the aspect ratio, you need to have, we are keeping that, I think, at like, I think it's like a 1 to 18, and the minimum is about 1 to 10, so the diameter of the column to your diameter of your particle.
Yeah, that's just that's a common thing of all column studies with media, but for sizing the RSSC, to change the EBCT is a function of process.
Yeah, but it's not just that model. It also, so this, if you want to look up the details, this is it's Manham and Rittman in 1992, and they actually did look at a full-scale plant and at their bench scale to see if you could use it. But yeah, so it also takes into account the microbial growth and attachment.
Right. Yeah. So it's. I mean, there's different options within the model, but it's a biomass-based model, making sure that you're comparing apples to apples, essentially, with the amount of biomass that you have.
Yeah. So it's going to be specific surface area.
I think that must be one of the key
That's one of them,
parameters.
yeah.
Yeah. There's 3 scaling criteria. Yeah.
Well, you probably want to have the film diffusion not be limiting, so you have the Reynolds number high enough to not be film diffusion limiting, and then whatever the next process that's governing, which in RSSCT is internal diffusion within the media, that's not it here, it's the biomass uptake, so it's got to be specific surface area. That makes sense.
Thanks. Anything else? Thank you, Emily.
This is Scott.
Hey, Scott.
Yeah, he probably knows this in space.
What
He
kind
doesn't
of
like this.
concentrations of geosmin were you using?
I'm spiking with 750 nanograms per liter.
And so did you allow the biomass to acclimate to the geosmin, because it oftentimes shows an acclimation period?
No, just acclimate to using SMPs.
So part of the lack of removal could be because the community hasn't adjusted itself to the utilizing that low level of geosmin.
Okay.
Yeah, I think what we were hoping to see, maybe our hypothesis just isn't right, but we were hoping to see a shorter lag where the organisms were first exposed to those complex SMPs as opposed to being exposed to the very simple acetate. We hope that would basically lessen that lag period. They'd say, oh great, another complex carbon source, we can get right to work on that. But that's not what we've seen so far, but we'll see what the second run says. Does that answer your question, Scott?
Yeah.
Okay, cool, thank you. So in terms of outputs and outreach, we had a presentation at the Biological Drinking Water Treatment Symposium just a few months ago. Scheduled, Emily's going to give a talk at Texas Water, which is a pretty large state conference, and Mahal is going to give a talk at ACE in June. In terms of what's coming up, we're planning on doing a white paper for the WINS website in the fall. We have several manuscripts. I'm showing 4 here, but I think we can probably get 5 to technical journals. And then we've worked with Bruce to schedule a webinar probably for spring 2017. So that's where we're going.
Out to California. Early on, as I was trying to make this go full scale from Parolo's side, it was a real challenge. Small or large utility. But as we've started to see different drivers show up, across the Midwest, as you know, ammonia concentrations 4, 5, 6 higher, you can't breakpoint that without causing, first of all, major chemical costs, and B, disinfection byproducts. And, the EPA has a 2 or 3 plants now, I think, at small systems for iron, manganese, ammonia. I'm seeing, and I think others are seeing, a much more welcoming environment now for systems that are biological, because they really can be automated. I think we're adding some good toolbox items to help operators know what to look for, but I think that some of the other drivers are becoming so acute in a lot of cases that we're seeing biofiltration make its way even to the smallest of utilities. We're starting to pilot in the Central Valley of California, which is for nitrate removal at a well that serves 4 houses. That may be an extreme, but we're trying to find that edge. They have no other options. They can't take ion exchange brine and take it anywhere. So historically, I agree, that's where it's been. There's been a lot of aversion to it, but we've seen a real shift in that over the last, I'd say, 5 years.
Is there a difference in whether it's looking to control regulated versus non-regulated contaminants?
Can be.
So you're talking ammonia, iron, why there's certainly going to affect the regulated contaminants like chlorine, breakpoint, but it's not like the arsenic and the perchlorate.
Right. So the acute drivers aren't there as much, but for example, a utility in Minnesota that we've been working with, they've been trying to take care of their iron or their ammonia. They don't really kind of ignored their ammonia. They tried to breakpoint it on the back of the plant, which is very difficult. But they have iron and manganese coming in. They have green sand filters, and those work great for a couple of years. And now they're batching those filters like every month with chlorine to try to regenerate the green sand. So their DBPs are off the chart. They have nitrification in the distribution system, corrosion problems in the distribution system, nitrite accumulation. They're tired of the complaints. So some of those drivers are coming into play for them now. think we'll see more of it. I don't know what you guys are seeing. In terms of biofiltration, most of the, as we discussed earlier, most of the small utilities are groundwater plants. So you don't think of biofiltration.
I'm worried about having to put too much on operators that aren't sophisticated enough, don't have the necessary tools, that this, in essence, yes, I agree that if this is a last resort, then we gotta go through it, but.
There's the education outreach component, no question.
Well, I was just gonna say, so I've done a lot of work with manganese over recent years, and I'm mostly physicochemical, but I'm interacting with fair amount with Eric Groton of Blue Leaf Industry. Eric really runs the only company, one of the few in the country that he only does piloting. That's what he does, goes around with pilots, and he's done biological iron and or manganese removal. And he has, over time, convinced himself that he's really, really high on this as an approach for lots of size utilities. And really, and I was talking about controls, if you can control chlorine dosing and coagulant dosing, you can control DO and pH. And that's basically it for iron and manganese in terms of control the environment.
That can be a big if, though.
But I mean, those two things, what I'm saying is it's not more complex than doing some other chemical dosing.
I know, and I know systems that have problems with pH and coagulant dosing.
Yeah, but I mean, if we're not gonna, if it's not riverbank filtration with no chemical addition, then we have to, there is a step we need to take.
Yeah, but there is some of that basic stuff that there are systems that are operated that can't even do the basics.
And that's going to be a problem for any
that's a different
plant.
Yeah.
In any type of unit process they're running. I don't think biofiltration is going to push that limit any further. It's a problem.
Ted, can you talk a little bit about operating at a distance? I mean, so remotely operating a plant. Like you have that capability right with your skids.
Yeah, and we talked about this earlier in terms of the different modes of operation for small utilities. In California, the Division of Drinking Water is really concerned about small systems, of course, through the Central Valley. Nitrate is everywhere, and I mean, it's Aaron Brockovich for nitrate today. I mean, it really is, and there's all kinds of news articles and bad press and on and on. Even the agriculture industry is now coming to engineering firms, into regulators, saying, okay, we need to come to the table now, which is really an amazing step. So one of the modes of operation, because these systems are becoming, like it or not, some of there's more turnkey, more packaged systems available for even biotreatment that are fully automated and fully controlled and monitored, data download from wherever you happen to be. So you can have a guy, gal sitting at a central control facility, watching 5 of them, and then goes out once a week to each of the plants to fill up chemicals and things like that. So it's a ways off, but the package type systems that are out there being developed, I can name 5 different biological denitrification package systems. It's really amazing how it's changed. That they are all automated, they all controlled remotely. So that's going to help, I think, any small system that if they're looking at biological treatment or any kind of treatment, the remote monitoring controls. Really.
I mean, I mentioned it to you earlier, and I mentioned Dave and John Passage. I'm also working with a catalytic denitrification system. Just, you pump in a little bit of hydrogen with an on-site generator, and denitrifies directly to dinitrogen gas. In standard kind of RO, standard membrane package, pressure drop of 6 psi.
Yep.
So that's something that really takes nothing easily, and so we're just starting to work with that. We'll be doing a pilot in Illinois starting later this year. Want to share. I think Chad D-Risk is also, he's involved in the project also, so he's working through that side. Also, so that's going to be an interesting comparison, non-biological.
There's also some new ion exchange, GAC-based ion exchange technologies too for non-biological.
activated carbon.
Yeah, the modified active
Yeah, a lot of
Looks
stuff.
interesting.
A lot of stuff comes out of Israel.
Yeah.
There's a big development center over there, and Chrome 6, all the organics. They have a technology.
Yeah, right.
Different companies have technologies that they're bringing into the United States and working into the market.
Yeah, it'd be very interesting to see a comparison.
Yeah.
I think that's in the next 3-year cycle.
Yes,
of the
right,
center.
right.
Yeah.
Very good.
Got it. Are there any other questions? Let's take